Welcome to the CSEC Explainer. Seriously, take a quick look around you right now. Non-metals are literally everywhere. From the oxygen gas in the air you're breathing this very second, to the water you drink, right down to the plants growing in the soil outside. Today, we're completely mastering Section C of your inorganic chemistry syllabus. We're going to break this whole thing down step by step so you can walk into that exam room feeling absolutely confident. Let's lock this down. Here's our exam blueprint. We're running through the properties of nonmetals, lab prep, real-world uses and pollution, water properties, treatment and green chemistry, and finally, a quick CSEC exam review. Section 1. What exactly are nonmetals? For this exam, we're focusing on hydrogen, oxygen, carbon, sulfur, nitrogen, and chlorine. Now, there's a huge contrast between their physical and chemical properties. Physically speaking, nonmetals usually have super low melting and boiling points, which is exactly why so many of them are just gases at room temperature. They're pretty poor conductors of electricity, and honestly, as solids, they look kind of dull. But chemically, they are completely different beasts. They react incredibly aggressively with oxygen to form oxides, and they react strongly with metals too. And that brings us to an absolutely crucial exam definition. Nonmetals act as really powerful oxidizing and reducing agents. An oxidizing agent is going to gain electrons during a chemical reaction, while a reducing agent will lose them. Notice how this whole electron transfer thing fundamentally dictates how nonmetals behave. Make absolutely sure you got this memorized for the exam. So, if there's just one single word you take away from this first section, let it be this: reactive. They might look a bit dull, but chemically, nonmetals are highly reactive. Moving right along to Section 2, laboratory preparation of gases. When you're prepping gases like oxygen, carbon dioxide, or ammonia in the lab, you have to follow a really strict chronological order. Step 1, you generate the gas. Step 2, you dry it. And Step 3, you collect it. But here's the catch. Your collection method depends strictly on two specific things: the gas's density and its solubility. So the magic word here is density. Along with solubility, density is the absolute ultimate deciding factor in how you collect a gas in the lab. Keep that locked in. All right, Section 3, real-world uses and pollution. You know, nonmetals are kind of a double-edged sword. On one hand, we rely on them heavily. Oxygen is literally life-saving in hospitals and used in welding. Carbon dioxide powers our fire extinguishers. Nitrogen and phosphorus are the magic ingredients in agricultural fertilizers. And carbon is the backbone of all our plastics. But on the flip side, they're responsible for some major pollution. Sulfur dioxide and carbon monoxide are choking our air, CFCs are messing with our ozone layer, and solid plastics plus excess nitrates are doing some serious damage to our ecosystems. The big takeaway here? Impact. Nonmetals have a massive, undeniable, ecological impact on our living systems, both the good and the bad. Next up, Section 4, the unique properties of water. Water is arguably the ultimate nonmetal compound, and it has some incredibly unique physical properties. First off, it's a universal solvent, which means it dissolves more substances than any other liquid on Earth. It also boasts a high specific heat capacity. That means it can absorb immense amounts of heat before it even gets hot, which is exactly how our planet's climate stays regulated. And super unusually, its density changes in a way that makes solid ice float on top of liquid water, keeping aquatic life safe underneath. Oh, and we definitely can't forget its volatility, which drives the whole water cycle. Now, because water is such an amazing solvent, it easily picks up minerals from the earth, and that leads to water hardness. Temporary hardness is pretty easy to deal with. You can just boil it away in a kettle. But permanent hardness? That requires actual chemical softening. Both types cause that super annoying problem where your soap just won't lather up, and both can lead to mineral leaching in your pipes. So grab your mental highlighters for this keyword: solvent. Water's incredible power, and the whole reason it creates things like hardness, comes straight from the fact that it is a universal solvent. Okay, Section 5, treatment and green chemistry. To actually make water safe for domestic use, the CSEC syllabus lays out a very specific 4-step purification process. First, boiling, to kill off any immediate pathogens. Second, filtering, which removes all the solid impurities. Third is chlorinating, to ensure all those lingering bacteria are totally destroyed. And fourth, softening, to deal with those dissolved minerals we were just talking about. But what about chemical pollution on a bigger scale? Well, that's where green chemistry steps in. By definition, green chemistry is the utilization of a set of principles that reduces or eliminates the use or generation of hazardous substances in the design, manufacture, and application of chemical products. Basically, it's about transforming a dirty, polluted factory process into something clean and eco-friendly. It's designing safer, smarter chemistry from day one. Our final takeaway word for the learning sections is sustainable. The ultimate goal of all modern chemistry is to build a sustainable future where we get the products we need without all the hazardous waste. All right, let's test what you know. Section 6. CSEC Exam Quick Review. Question 1. If ammonia is highly soluble in water and it's less dense than air, how should it be collected in the lab? Got your answer? Okay, because it's highly soluble, you absolutely cannot use water displacement. And because it's less dense than air, it's going to naturally rise. So you must collect it using upward delivery. Let's try question 2. Explain the key difference in treating temporary versus permanent water hardness. Remembering the difference from earlier? Temporary hardness can just be removed by boiling the water. But permanent hardness cannot be boiled away. It strictly requires chemical softening. Last one. Question 3. How does green chemistry aim to change traditional manufacturing processes? Well, the primary aim here is to completely reduce or eliminate the use and generation of hazardous substances, right from the very beginning in the design phase. Awesome job! Let's wrap this whole thing up with a really quick summary of everything we've conquered today. Number 1, nonmetals are highly reactive chemically, acting as powerful oxidizing and reducing agents. Number 2, gas collection in the lab is entirely dictated by its density and solubility. Number 3, while they're incredibly useful, nonmetals have a massive impact on our world through pollution. Number 4, water is a remarkably unique universal solvent. And number 5, green chemistry is the sustainable future of our planet. So I'm going to leave you with this thought. If green chemistry is the key to our future, how are you going to use it to solve the pollution challenges of tomorrow? Keep setting hard, and I'll catch you in the next explainer.